Hello everyone, and welcome back again to the Sports Biomechanics lecture series. As always, supported by the International Society of Biomechanics in Sports and sponsored by Vicon. I'm Stuart McErlain-Naylor from the University of Suffolk, and today I'm joined by Nick Gallimore, who is a life sciences application engineer at Vicon. And Nick's going to take us through a live motion capture demonstration, including live and post-processing, as well as real-time biofeedback. This is actually the second demonstration lecture that Vicon have provided, and it absolutely works as a standalone lecture. But if you enjoy this, then please do go back at the end and check out the previous lecture by Gait. So yeah, a huge thank you to Nick and Vicon, and I'll hand over to Nick to tell us a little bit more.
Hi Stuart, and thanks for the introduction, and hello to everyone tuning in from home. My name's Nick Gallimore. I've been a life sciences application engineer since 2017, and in that time I've had the pleasure of travelling around the world installing Vicon systems and training the end users on how to use them. Before joining Vicon, I completed my Masters in Sports Biomechanics at Loughborough Uni, which is when I was first introduced to motion capture. Also, coincidentally, I was a mocap subject for one of Stu's research projects during my undergrad. There are many elements to consider within an optical mocap system. Hopefully you all saw this banner going through Twitter. Here it is again as a still. The banner depicts the full life science motion capture pipeline, which we intend to walk through today. Our aim has been to give an introductory overview of what an optical motion capture pipeline looks like, splitting it into 4 sections: hardware and software, mocap modeling, actual mocap, and beyond Gait. Jacques covered sections 1 and 2 previously, and today we are going to look at sections 3 and 4. To recap the previous session, Jacques looked at hardware and software used in motion capture. We learned that a range of cameras have been developed over time to today's range of Vantage and Vero cameras, and how cameras are picked based on your research application and the capture environment. The software is arguably the most crucial part of motion capture, and Vicon Nexus has been developed to streamline data processing down to a single click, with customizable pipelines which include auto-labeling, gap-filling, and modeling tools. Jacques also explored biomechanical modeling, including what is modeling and why do we need it, how can we create a model, and in the context of today's lecture, how is it applied to motion capture. Regarding mocap modeling, there are various marker placements and out-of-the-box models available, and the model you choose can have significantly different results. The example used in the last lecture looked at hip joint center calculation from various methods, which I intend to demonstrate today. If you missed the lecture, feel free to catch up from Stuart's YouTube channel. Let's start looking at what's in the lab then. As we've previously advised, your system should be customized to suit your research application and capture environment. In our system, we have 16 V5 optical cameras and 2 view reference video cameras to cover a volume size of 12 meters by 5 meters at a height of 3 meters. When setting up your system, it's important to remember a marker needs to be seen by at least 2 cameras so it can be reconstructed in 3D, and so it's important to optimize the position and aim of each camera. The cameras also need to be in focus, and the aperture needs to be set to maximize the camera range whilst ignoring any background noise, and the software we'll be using is Vicon Nexus. Many labs also require integration with third-party devices. These may be via analog signals, which we can capture through the Vicon lock, or some manufacturers also provide digital plugins for seamless integration with Nexus. Today I'll be including Delsus EMG, 3 force plates from AMTI, Kistler and Bertec, and Vicon's Blue Trident IMU. To finish setting up the system, we have to calibrate the cameras and set the volume origin. Here we have the active wand, which is our calibration device. This video shows the calibration process, which typically takes a couple of minutes. You can see that each camera is collecting refinement frames, and once enough frames have been collected, Nexus merges the cameras in 3D, like so. Finally, we set the volume origin, also using the active wand. This defines the global coordinate system. If you have force plates in your system, they need to be aligned with the global origin, so it's common practice to set the global origin on the corner of an integrated plate, as you can see here. You can also see that the 3D markers have been overlaid on the video reference cameras. Now that the system is ready, we need to prepare our subject. This includes taking anthropometrics, such as height, body mass, leg length, knee width, ankle width, and so on, and applying a predefined marker set. Here we have the plug and gait marker set, which will be used for gait analysis. Custom marker sets can also be applied, such as using clusters. Let's get into mocap then, from capturing the raw data right through to processing our trials, running a biomechanical model, and displaying human kinetics and kinematics. During the demo, I will capture and process some simple gait data to show the motion capture pipeline using the conventional gait model, and then I will capture some functional movements and calculate the hip and knee joint centers using SCORE and SARA. So I'm going to change my webcam now so that you can see our volume, and I'm going to switch my screen so you can see Nexus. Firstly, let me introduce you to our participant today. This is Emily. The first thing that we need Emily to do is go into a motorbike pose so that we can capture a short static trial. This only needs to be for a few seconds long, and now Emily can relax. I'm now going to open up that static trial where I can reconstruct the raw markers. Traditionally, we would used to manually label every single one of these markers, like so. However, with Nexus's auto-labeling algorithms, we can do this automatically. This auto-initialize pipeline labels, scales, and calibrates our subject. Whilst we're in the static trial, we can also run the plug and gait static pipeline. Here we have the options to output joint centers and assume that the feet and head is horizontal. And as you can see, we get our model outputs generated. I'll just save the trial, and now when I go live, you can see that our subject is being labeled in real time. We also have the option to see a 3D overlay within the view reference video cameras. We can also show you the third-party devices that we've integrated with. Firstly, we can look at the force plates. Here you can see the ground reaction force from both the AMTI and the Vertec plates, and as Emily shifts from one plate to another, you can also see the force vector being generated. Next, we have the Dalsys EMG system. Here we have sensors attached to the left and right gastrocnemius, and as Emily plantar flexes, you can see the muscle activity. Finally, we have our blue trident sensors also attached to the left leg, where you can see the global angles as Emily knee flexes. We can now go on to capture our Gait trials. So Emily, please can you come to one end of the lab? That's great. And I'm going to set my pipeline up to automatically capture the trials as soon as she starts to be labelled. So Emily, in your own time, please walk from one end to the other. Hand back. And let's get a couple more. That's great. Now that we've captured our trials, Emily can now relax and take a seat as I demonstrate dynamic processing. So you load up your Gait trial and you reconstruct and label the markers that you need. Here you can see that the left plate has been correctly identified. We can also assign the right plate to the right foot. Next we check the quality of the data. At the moment we've got 274 gaps. Some of these will be at the beginning and end of the trial, so we can crop the trial to a useful area. And all of the remaining gaps can be filled using our gap filling tools. For example, on the lassie. We also have an automatic gap filling tool which does the job for you. The last thing to do is to run the dynamic plug and gate model or pipeline, which filters the trajectories. It detects the foot strike and foot off events from the force plates, autocorrelates these, and then it processes the dynamic plug and gate model, as you can see. All of these steps can then be put together in a single pipeline to make it possible to process this data with a single click. I'll demonstrate this on the second Gait trial. As you can see, the trial has been fully processed from a single click. If you have multiple trials in your session, you can apply the same pipeline to all trials one after another using batch processing. Additionally, we can transfer our videos so that we can view them as a 3D overlay. Now that the trials have all been processed, I can open up one of my trials . and I can zoom in on my markers. You can see that the hip joint centres have been output. These have been calculated using the Davis method, as Jacques talked about last week. We can view all components of the system at the same time. Including the video overlay. Now that we have the hip joint centres calculated using the plug and gate model, we can also calculate them using a functional method. So now I'm going to go back live, where we will record Emily doing a functional motion in order to calculate the hip joint centres and the knee axis of rotation using the score and SARA method. So now we're going to record the functional movements required for calculating the hip and knee joint centres. Here you can see the hip movement called the star arc movement on the left and right leg. And also the knee flexion extension, also on the left and both legs. These movements can be broken down into individual trials, but for today's demonstration we're just doing it as one step to simplify things. Once the trial has been captured, I can then load that back up and I can reconstruct and label the trial as we have been doing already. We can now check the trial and make sure that we are happy with the movements, and we can do any gap filling that is necessary. Once you are happy with the trial, you can then save it, and we can go on to process the score and SARA. Before we can calculate the hip joint centre and the knee axis of rotation, we first need to calculate what we call OCST bones. OCST stands for Optimum Common Shape Technique, and we do this on the static trial rather than the dynamic trial. So I'm going to load up my static trial, which has already been reconstructed and labelled, and I'm going to go to my Pipelines tab, and I'm going to find my Advanced Gait Workflow Static Pipeline. In this pipeline you can see that we have Calibrate OCST pipelines for each segment. After running that, you can see that there have been additional bones placed onto my subject. Each one of these resembles or represents a different segment. I can now save that trial, and I can open up my functional range of motion trial. And in my Pipelines tab, I can now run the advanced gate workflow calibrate pipeline. Now when I zoom in on my subject, I can see that these functional hip joint centers have been placed in, and the knee axes of rotation have also been calculated. We can now apply this functional method to our walking trials. So I can save my trial and I can reopen up one of my previous gait trials. Since this trial has already been processed using the plug and gait model, you can see that there are hip joint centers already present as calculated using the Davis method. I will now calculate hip joint centers using the functional method by going to my advanced gait workflow dynamic pipeline and running that. You can see that the hips have now been placed into the 3D mode, into the 3D view, and the knee axis of rotation are also available. As you can see, there is a significant difference between the two methods in calculating the hip joint center. We can also view this in a graph. With the trial now fully processed, we can view our kinematic and kinetic data using Vicon Polygon. So I'm going to create a new report in our data management, and I'm going to open up Polygon. I've already created a template for this, so I'm going to click yes, and I'm going to select my template. Now I can easily load the trials into my report. And I can view the kinematics for each trial by clicking on the hyperlinks. We can also view a comparison of all the gait trials. As well as the kinetics. Here we have the moments at the knee, the hip, the ankle, and the ground reaction force moment. Additionally, we can look at 3D analysis. Here we have our skeleton walking through the gait lab, and we can see force vectors also. We can also compare trials in a 3D view. This may be useful for comparing pre and post surgery or rehabilitation intervention. Finally, we can look at video analysis using the reference video cameras. Here you can see the skeleton has been overlaid on top of the video. In the previous session, Jacques also talked about the modeling options available to us. Here I have a Python script which takes the kinematics, it normalizes the data for each gait cycle, and it displays them in a PDF. I can run this script through a Nexus pipeline like so. As you can see, the PDF has been generated, which displays the left and right average data, the left cycles and the right cycles. If you are interested, this script can be available on request. This brings us to the end of our practical demonstration, and I'd like to thank Emily for being such a great participant. Usually I'd ask the audience now to give a bit of a round of applause, but since this is a virtual demo, please can you all give Emily a big thumbs up by clicking the like button. Now let's move on to the fourth and final piece of the pipeline, which is mocap beyond the Gait lab. We have, for the sake of simplicity and making it easy to follow, captured some very simple locomotion in this demo. There are multiple other applications within the life sciences market where Vicon is used, so let's take a look at them. Here's a 3-minute video that will take us through some of the biomechanics research beyond the Gait lab. I hope Stu doesn't mind us taking this from his Twitter. Here's one of the Life in Pictures, which shows a great looking setup for badminton. And of course another speaker on this series, Dr. Paul Felton, showing a setup beyond the Gait lab. We are very happy to work with many customers in this field of biomechanics, and we welcome new ones to come who will continue to push the boundaries. Jacques talked of Vicon operating in what we define as 4 distinctive markets: life sciences, entertainment, engineering, and location-based virtual reality, or LBVR. All of these groups use the same types of hardware. However, Vicon provide a unique software platform for each market, enabling the users in each sector to focus on the data in a meaningful manner for their area of interest. We have looked at mocap across life sciences. Let's now take a quick look at other areas. The first market I will showcase is the VFX market, making of film, games, media, and so on. Here is a 2-minute clip of our latest show reel, which I hope you will enjoy. The third market we define is engineering, which is typically dominated by drone tracking. Here's a show reel of some of that. But equally, this market has sections of ergonomics that translate to biomechanics really well, where heavy industry, such as car manufacturers, look at the ingress and egress of cars, or indeed NASA looking at their spacesuits. The fourth and final market is a relatively new one, around 3 years now, where the combination of motion tracking systems, the latest VR headsets, and backpack PCs deliver the latest out-of-home entertainment called location-based VR. There are around 150 of these types of venues around the world currently, and before COVID, it was looking like adding a few zeros to that number in 2020. With the hopeful return to normal coming, more of these will spring up.
Imagine a world where you are the star of your own movie. That's what one company is promising. Dreamscape Immersive is a new virtual reality experience that uses state-of-the-art technology to transport viewers into an imaginary world.
It's a way of using VR that's really quite revolutionary. We are able to take your whole body and actually turn you into an avatar and put you into a richly detailed digital world in which you sort of become the star of the movie.
Guests suit up head to toe in VR gear and enter a room.
Are you guys ready? Yeah. All right, let's go inside.
They watch as their bodies transform into digital avatars. In the virtual world, they must work together by interacting with their surroundings if they want to reach the end.
We make experiences that merge the emotional value or the emotional impact you get from a good Hollywood movie with the visceral thrills you get from a theme park ride.
Finally, I'm going to squeeze in one last video from last year when we celebrated our 35th anniversary. Thank you for watching our mocap seminars. Please feel free to send any questions to support@vicon.com and subscribe to the new Vicon Life Sciences channel on YouTube for the latest video content. I'm now going to pass you back over to Stu to hear what's coming up next in the series.
Thank you, Nick. That was really, really good. I'm hoping that can serve as a really useful resource for anybody starting to use motion capture or anyone starting to use Vicon in particular. But even for students, when we talk about motion capture, especially at the moment when lab access is limited, hopefully that'll be really useful. But I know I definitely got something out of that, and hopefully right through from students that have never seen motion capture through to people that use motion capture on a regular basis. There's hopefully enough there for everyone to A, learn something, and B, hopefully spark some ideas about possible future uses. So yeah, thanks once again for that. It's really, really good. And thanks to yourselves, Jack and Andy at Vicon, for all of their ongoing support through this series. And that just leaves me really to say thank you to everyone for watching. And please do check out the upcoming lectures that are on the screen now, as well as those that have already been if you've missed any. And please do subscribe and click on the bell to get notifications and stay up to date with what's going on in the lecture series. Thank you very much.